Okay, guys, this is example number 7 that we got a little bit derailed on this morning about the trains going from New York to Boston. So I wanted to work through that for you. It's not exactly fast or quick. It's a little bit involved algebraically, but this is just a more full explanation of what's happening in the answer key in the back of the textbook. So first of all, the question is, okay, the trains are 221 miles apart. They leave at the same time, and they gave you the time it takes for them to travel the whole route. And we want to know when are they going to cross paths. So we have a lot to figure out. The first thing we have to do is recognize, okay, they gave us the distance in miles. We're going to convert that back over to meters. So just if you do a quick Google check, you can find out that there are 1,610 miles in meters in a mile. So we multiply here and we'll find out this is the number of meters that each train is traveling. Then we want to figure out what are the speeds that those trains are traveling. Just for reference, everything noted with an A, denoted with an A, refers to the train that goes from Boston to New York. That's the first one mentioned in the problem. And anything noted with a B is the train that goes from New York to Boston. Okay, so the time that it goes from Boston to New York, train A, is 220 minutes. Multiply that by 60, and this is the number of seconds in scientific notation, right? 3 significant figures. And train B that goes from New York back to Boston takes 245 minutes, so this many seconds. Then we can figure out the velocity, the average velocity of each train. We're assuming they basically have a constant velocity the whole way, so their average velocity is the same as their constant. So average velocity of A, remember the horizontal bar on top means average velocity, would be the change in position, displacement that we found at the beginning, divided by the amount of time that train A takes, which we just found, is 27 meters per second, and then same process for train B. Then we get into a bit more confusing algebra here as we try to figure out what our actual distance is going to be before they meet. Okay, so the total displacement here for each train we know is 221 miles, but when they meet in the middle, they started at opposite ends and they meet somewhere in between, then the displacement of train A plus the displacement of train B would have to equal the total length of the track, since they started endpoints and covered everywhere in between where they meet in the middle. If we just do a little rearranging here, we can subtract the delta xb from both sides, the displacement of train B. We see the displacement of train A equals total displacement minus train B's displacement. And then the textbook gets into a weird note where it says the ratio of displacements has to be equal to the ratio of velocity. Why is that true? We know velocity is always displacement over time. Cross multiplying, this means displacement is always equal to velocity times time. This is kind of a general rule that's worth noting, that displacement always equals velocity time. It's not in our formula sheet, but it's a useful thing to keep in mind. How fast you're traveling times how long you're traveling equals how far you've traveled. With that in mind, if we have the ratio of the displacements, well, the displacement of A would have to be equal to the velocity of A times time, and the displacement of B would be equal to the velocity of B times time. But we know it's been the same amount of time since they left because they left at the same time. So those two cancel each other out, and we get that ratio right here. And now here's the key idea. This is where the algebra comes in. We have one equation for that involves displacement of A, and we have this second equation that involves displacement of A. So these two different equations can be used to do substitution using a system of equations. So where we see displacement of A, we're actually going to just replace it with this expression right here. And then that leads us to this step right here. From here, it's a lot of algebra steps. So I don't want to sit and explain all of them, but I would encourage you to work through these ideas here. But basically, we're going to cross multiply from here to here. Then we're going to distribute. Then we're going to we're going to move these terms right here. We're going to move this term right here. We're going to move it over to the other side, which is going to allow us then to find a common factor, right? This is a common factor. And once we take out that common factor of delta xb, we can divide all this junk out, and we see that delta xb is equal to this guy. And we actually know all of these quantities. We found delta xt. We found that right up at the beginning, right? That's the total displacement. We found that up here. We also know the velocity of B, we found that earlier. We know the velocity of A, found that earlier. And the velocity of B, we found that earlier. And I miswrote this here. These aren't multiplied, but added. And then we can just go ahead and type this all into the calculator, and we'll get our 1.68 times 10 to the 5th, which is the total displacement of train B. That is the train that goes from New York toward Boston. So that would be, that's what we're seeing right here. Sorry for the bell. That's what we're seeing right there. And just subtract it from the total displacement to figure out what the displacement of train A is. Okay, so it's not like a simple, straightforward problem. It's a lot going on there, but hopefully at least you can kind of follow the process there. This is like very high level. Don't expect that this is going to be like a typical test question. This is a very high level question, so don't panic if it's like kind of confusing. But there's a quick rundown of number 7 from the homework that we struggled with a little bit this morning.